So, this video, as per the title, we're going to start looking at wings, or at least lifting areas might be the best way to put it. There are a number of places where we have lifting points, and those are really to do with the wings, the vertical stabilizers, and on other aircraft, the kind of the tail planes. Now, obviously, you have other things that have lift associated to them, or wing in Unity sense associated to them, but those are moving parts, and we're not going to consider them today because those have their own special setups and designs, etc. So, really, when we talk about wings, the thing we need to be aware of is that there are, I guess, three main components. So first off, what we'll do is go and look for some wings. So we type T:\wing at the top in the search bar. It will give you any part of the aircraft or any part of an object that has a component of a wing on it. And you can see you've got body lift aero here, vertical stabilizer aero, then you've got the elevons, then the flaps, then the rudder, elevons, flaps, wing. Okay, so if we click on a wing, for example here, and we look at it from side on and top over, you can see where it's lined up. See one side, on the other side. Okay, so that should be fairly easy to understand. So really what we're looking at here in terms of the wing is what affects the wing and how we're going to make changes to this. So in terms of the wing, what you effectively got is a number of variables. Most of them are not very useful, but the ones that really are useful on here are lift coefficient, drag coefficient, lifting area, also the aero profile potentially, depending upon what you're trying to do. Everything else you can pretty much leave alone. And that's the same for every kind of wing. So if we look at, for example, the verticalized stabilizer, it's the same thing. It's exactly the same thing. So all we need to do now is decide how we're going to adjust these. So really, when we're looking at them, the two that are easy to resolve, I suppose, or the one that's really easy to resolve is lifting area. Lift coefficient really come down to the shape and the style of the wing, and you can find sometimes information about this. However, it's really difficult to find anything that's going to make any sense to what you're trying to put into this number here. You can do a lot of research and find that lift coefficients change with various things. They change with height, they change with speed, etc. And trying to find something you can plug into here is really difficult. I would not try to do it that way necessarily. Or I might try and find out a rough number if I can, to say what it would be at level flight at kind of sea level-ish, and then utilize that to kind of work out what it should actually be by a bit of testing and experimentation. So that's the first thing. Drag coefficient affects how much lift you can get from the wing, but also it affects the potential speed of the aircraft. Because if you've got high drag on the wing, obviously it will make it incapable of flying at bigger speeds. And then lift area. Lift area is really a function of a number of things, I suppose, is what you need to be aware of. It's a function of the shape. So in this case, we've got like a kind of a delta-y shape, but not really. It's a function of the size. And it's a function of how much it's swept back. So, for example, aircraft that have delta wings tend to have much lower lift compared to the size of them. Now, that's offset by the fact that delta wings are better stable in stability terms and give you other advantages, but it does mean that there's a lower lifting area. And we have some calculations we can do for that. It's a really simple calculation that we can do for that. That gives us a very good approximation for these numbers. So what we need to do really is decide how we're going to work out what those figures are. As you can see here, we have a picture of it, but how you know from that exactly how big those are is a different thing. And there are different ways you can do this. You could try overlaying it on a graph square or something on a Word document and counting up the squares, any of those kind of methods. I personally actually utilize an online tool called Sketch and Calc. And Sketch and Calc allows you to bring in a picture from online, paste it into the browser, and then work out how big things are. So I'll show you that method. If you want to work out other ways, there are other ways I'll explain afterwards as well of finding these things out that may be useful. I'll give you at least a starting point to work from. So based upon that fact, what we need to do really is decide how we're going to, which ones we're going to work out. Now, with wings, just a quick thing on here actually. You can see they're aligned here. I would always try and make my wings kind of towards the frontish and inner part of the wing rather than out on the edges. It's just, there's no advantage to moving them around massively. The game doesn't really recognise them in that way. It just looks at how much wing and how much coefficient you've got. It doesn't really look at anything else. So you don't really need to worry about where they line up. It's just easier to do it this way, is what I always found personally. So based upon that, what we're going to do is say, okay, well, those are in the right location. Make sure they're lined up, obviously. They need to be roughly in the right place compared to each other. And mine are, I mean, there's slightly tiny differences just because of the way that it works, but these numbers are so small here, it's not worth worrying about. So hopefully that should help with that piece. Just a quick one of the discussion here is around the fighter wing aerodynamics, just because it's an interesting discussion. Normally, I'd say for most aircraft, leave it with the standard fighter wing aerodynamics. If you really want to get into detail about making it feel like the exact aircraft, you can do. I have done it. I'm probably the only person that will ever do it. But you can set these up so they are like the real thing. Now, if you come in here and look at fighter wing aero on here, you can see that, well, there are two versions actually, funnily enough. There's a version for fighter wing aero and wing aero. If you look at fighter wing aero, it gives you a bunch of numbers in here, or 3 curves and a bunch of numbers. The ones you're really interested in are lift curve and drag curve for any aircraft. I did it for the Mirage as an example because Delta wings have a very, very specific style and very specific usage, and make aircraft feel very different. So I purposely went out and looked up lift curves and drag curves for Mirages, or for Delta wings specifically, and then adjusted these in here. And they actually give you a multiplier for the coefficient compared to the angle of attack. The same on the drag curve, it's also the same. And that will affect how the thing flies. Again, most people, not a big worry, most people won't even touch it. So first things first, I guess. What I've done here is I've got my picture here from above of the F-117, because we need a picture of the F-117 from above for what the tool I'm going to use it for. I've also included in here this little cube, and this cube is actually just a 1 meter cube. I'll show it outside the box as it goes because it's no longer needed there. But it's just a 1 meter cube set at the same height and area as the aircraft, so I've got a kind of a way to scale it and to understand how big this actually is. So what I'm going to do is I'm actually going to come to the bottom here and use the snipping tool. See, I've done it before actually recently, and take my picture, and then I'm going to go to Sketch and Calc. So copy that, and I'm going to go to Sketch and Calc. I then post my image into Sketch and Calc. So this is called sketchandcalc.com area calculator app. So I've pasted my image into there. And next I need to set the scale. So to set the scale, I use a little measuring tape, and I draw along the edge of my 1 meter cube. And when it asks me to specify, I put 1 meter. So now it knows that that's 1 meter across. Click out to canvas. And if I now zoom in, I can use a little tool here, the line tool. These are the tools you can use actually if you want to. I don't think I've really ever used many of the other ones because this is the most useful one. What you do is you draw around the edge of your aircraft. So I draw from there to there, to there, to there, to there. I'll draw across the back here because of the way that this design comes in. To there, to there, to there, and back to there. Okay? And if we now look in the bottom corner over here, it's giving us roughly a figure of 69 meters squared, 68 meters squared actually. So that's interesting. We've got 68 meters square wing size. Now, obviously, that's 2 wings, strictly speaking. So we need to split that in half to make 34 meters squared in each one. The other thing we can do on here, which we really need to know, is also what this angle is at the top. And you can see if I zoom in on here and scroll around a little bit, we end up with 45 degrees as that angle. So 45 degrees in there. That's the other thing we need to know about. So we've now got 34.17 meters squared and a 45 degree angle. Okay, so now we know that. That's really simple. You can work this out any other way you want. You could use like an overlay of grids and squares, or there is another way I'll explain to do this as well. That might be more useful if you can get it, or you can get the information. So the calculation that we need to work out what the lifting area is of a wing is 0.5 multiplied by the wing size in meters squared, multiplied by cos, which is the cosine, bracket wing sweep to the power of 2. So first off, we put the calculation in. 0.5 multiplied by 34.17 multiplied by cosine. Well, wing sweep is not... So earlier on we looked at this picture here, if you remember, and we said it's 45 degrees. So we're going to have to half that first, so that's 22.5 degrees. But it's not that bit actually, because that bit is this angle here. What you need to know is what that angle is there. So the way to do that, really simple obviously, is we say it's 90 minus 22.5 degrees all squared. Okay, so we start working that out. We come into our calculator, clear it. 90 minus 22.5 equals 67.5. Do trig, cosine of that is 0.3826, and if we then square it, is 0.14644. So 0.14644 you should be able to see on there obviously. So now we have 0.5 multiplied by 0.146444 or something, was it? 446. Okay. And 34.17. So now if we do that calculation on the calculator, multiply that all by 34.17 equals that, and then multiply it by 0.5. So we end up with 2.502, or 2.5, whichever you want to look at that, which equals 2.5. And that's actually the figure that we need to put into Unity for our wing right arrow. 2.5. Okay, as simple as that. That's all there is to do, strictly speaking, on that bit. Let's just go and actually have a quick look at the wing left part and do the same on there, so we remember to do it. 2.5 in here. So the other way you could try and find this information is you could come to Wikipedia or wherever else you can find your vehicle, and in actual fact it says here that they reckon the wing area is 72 meters squared, and that's actually coming directly from Lockheed Martin. In which case I might be willing to accept that they might have a slightly better view of it. Now I suspect that the angle's the same, but we could probably look it up. Could do wing sweep F117 high sweep angle. It reckons 50 degrees actually. Okay, you reckon 50 degrees. It's okay. So we can go back and do those figures instead. So let's do it that way. 0.5 multiplied by 36 multiplied by cos 90 minus 25 squared. What does that give us? Be interesting. So clear that up. 90 minus 25 equals, do cos of it, and square it up is 0.178606, 0.178606. So 0.5 multiplied by 0.178606. We're going to do that multiplication through. Multiply that by 36. Multiply it by 0.5. This gives us a slightly bigger figure of 3.2. Okay, so given that that's what they tell us it is, I'm going to assume that Lockheed Martin probably know better than me. 3.2. Now, in terms of the lift coefficient, it's always really difficult. I'm going to state that this has a relatively low wing coefficient. The F-117 isn't well known for being overly stable, but it's not hideous either. So I'm going to go for 0.25, just based upon what you hear about that as a vehicle. So we have now set the lift coefficient. I'm going to leave drag coefficient as it is. It's probably about right. But we've now set the aeros on there to be 3.2. And that's actually not too bad, relatively speaking, if I'm being honest. It's not the worst. Certainly. What we then need to do is look at T:\wing. And the only other ones we're really interested in is body lift aero. Now, because we've not really got much more body than this, I'm actually going to say the body lift area on this is going to be 0. It just hasn't got any other body. It's all wings. So I can ignore that one. Now we've got left vertical stabilizer aero. And this is where we get slightly into, do you want to create 2 or do you want to have 1 for it? Depends what you're going to do with your vehicle. If you're going to have stabilizers that are going to be damageable, for example, and this model doesn't include any damaging stuff, but if you were going to do that, you could set it up so that it has different stabilizers and all that kind of stuff. One of the things just to note actually is you need to make sure that the green axis, which is pointing upwards here, is the lifting direction for your wing. As a rule. Not always the case, but certainly most. You want to make sure that that's the case for the wings. So okay. So yeah, so we've got that one. I don't think any of the other ones we need to worry about right now because all the others are just bits and pieces. In this particular case, I'm going to be a bit lazy here, if I'm being honest. Actually, no, I'm going to be a bit lazy maybe. Let's have a quick look at it. Let's just have a quick look. So if I do a maintainer and find what else does it link to. So it doesn't actually link to anything else. Okay. Which is slightly surprising, if I'm honest. For the aero. Is there anything linked to that? There isn't anything else linked to that either. Right. So we could do it, I suppose. So what we could say is, okay, let's have a look at this one then. So we've got the vertical stabilizer there. What we could do is do a similar type of thing. And say, how big is that likely to be? Well, it's likely to have a low lifting area, relatively. So we could do the same on this one. We need the cube though. And the cube here. So it's a bit awkward. I'm going to do it from there because it's probably for the amount of difference that's going to make. Probably not worth worrying too much. So we take a picture of it. And work that out the same. So I'll do that off screen. So for the vertical stab, what we have is 0.5 multiplied by 3.2 by cos 64 squared. So let's go do that. 64 cos, square that, multiply it by 0.5, multiply it by 3.2 is 0.3. So it doesn't have a massive lifting area. So if we go to vert stab, do 2, and what we'll add is we'll keep the lift coefficient of those quite high because of the way that they angle into the to the airstream. We'll keep that quite high, and what we'll do is actually create another one. So we'll duplicate this now, duplicate it, and call it right stab arrow, right vert stab arrow. Okay, so these are in exactly the same position obviously right now. So what we need to do is first go over the top, move this one to be in line with the left stab, and then move this one to be in line with the right stab. So what I want to do though is I want to look here and go, okay, well that's minus 12.1, so that should be 12.1. That's minus 37.1, and that will be the same actually. Okay, so those are there. We now need to move them both down because they actually want to be in line like that. And then what we need to do is actually angle it so that it's in the right place. So what we'll do is rotate it around Z so that they face at an angle the same as roughly as the vertical stabilizer, as you can see there. And that is 126.26, which actually will be the wrong way, but that's fine. Because what we can do is say 360 minus, that'll be the right angle. So you can see that the green points away from the lifting area there, and you want it to be pointing in that direction. So now we have two vertical stabilizers. That's going to annoy me that that's spelled wrong. So we have two vertical stabilizers and we have two wings, and we have them all correctly set up. So that should now be a perfectly flying F-117. So we can probably go and test that. Okay, so now we're inside the game, and we'll load up the F-117. Load. The pilot. Start it in the air. Still have the low over there. And this should be an interesting setup. What we might run into here is that the aircraft might be very unstable and we might need to fix a flight assist. Now the F-117 had an awful reputation, if we're being honest. Maybe undeserved actually from what I've read, of being quite unstable at low speeds. It's also got a terrible reputation for being not very fun to fly. Which is understandable when you actually look around the cockpit, maybe. And it's quite tiny inside, I suppose. And you're often doing long range missions, etc. Now, I wouldn't expect this aircraft to move very quickly. I would not expect it to turn very quickly. That's just not the kind of aircraft it is. Let's be honest. So it does look like we're going to have to do some changes maybe at some point. Because it is very, 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 very unturny and what have you. So maybe we need to update the lift a little bit on this. But anyway, it's kind of what we expected. Well, it's kind of what I'd expect, if I'm being honest with you. Let's put a bit of power into it. Get it doing its job. There you go. We now have our perfectly working F-117.